Morning, guys. So, welcome to our second lesson on energy. Yesterday, we started looking at energy sources. A useful energy source was one that was able to release energy at something that's a reasonable rate. It's nice if it has the added benefit that it produces minimal pollution. We talked about sources being either renewable or non renewable. The reason why we rely so heavily on non renewable sources is because they produce high quality energy. It's really concentrated energy. We're always fighting this losing battle. Although energy is always conserved, the total number is the same. Given the amount of heat that gets released off, the quality of the energy is constantly being degraded, it dissipates away, it spreads out, and it's no longer available for use. A non renewable source here generates that high quality energy. High quality energies will have a high energy density. They're going to produce many megajoules worth of energy per liter of the fuel that it takes. Or we can convert that, we saw with our practice example, through the actual matter density. We can actually convert to specific energy. If I'm thinking about how heavy this fuel source is, I can use density to interconvert between the two of those. We want to generally focus more so on renewable sources. So, because the coal and the petroleum products here, they take millions and millions of years to form. If we use up them too quickly, that's a finite reserve. Whereas if I do a more alternative source, if I can harness wind energy, solar energy, if I can harness water energy, hydroelectricity, that would in the long run here be better for our environment and also be a more long-lasting energy source. So today we're going to take a look at C2, which is on fossil fuels. This one here is our finite resource. This one here is a non-renewable source. But if you think about all our transportation needs, cars, planes, a lot of refineries need fuel, oils, gasoline, things like that. All of them are down to these fossil fuels. Let me just flip through those two slides from yesterday as well. Fossil fuels, like we said, from millions and millions of years ago, we had plants. They had photosynthesized. They were biological compounds that had the typical organic compounds, C, H, N, S, and O. Over times of being trapped millions and millions of years ago under high pressures, high temperatures, they gradually get reduced. Oxygen is one of the chemicals that lose much quicker than some of these other elements here, and we end up eventually forming fossil fuels that are primarily hydrocarbons, although unfortunately those hydrocarbons are just a big mess. It's just all mixed up together. It's not necessarily useful unless we can somehow purify them. So I mentioned these two comic strips here. If you look just two primary words for coal, we're specifically looking at in swamps or land-based things here. Sure, later on it might get layered over by water or whatever, but it started off from sort of living land plants. They get buried over millions of years. They form a nice coal deposit, layers and layers of coal. Whereas if you compare it to petroleum, which is also under the fossil fuel umbrella, petroleum here focuses mainly on aquatic creatures here. When the plants and animals died off, they also get buried over layers and layers, and over these enormous heat and enormous pressure, it turns into oil and gas. We typically have oil refineries that do sort of deep sea digging or land digging here. It's mainly just one broad stroke here. We can say one is mainly to take some coal out of the ground, the other is to take petroleum products. So as we take a look at petroleum products and some of these eventual gasolines that we harness from petroleum, our big idea for this section here is petroleum is actually a complex mixture of hydrocarbons. So hydrocarbons that range in size from C1 all the way to C200, even probably heavier than that. What we're going to learn in this lesson here is how do we purify them? How do we separate them in such a way that we can actually use them for the different fuels, for the different needs that we need. So we're going to be able to separate these fuels here by running them through what's called a distillation column, and the technique in general is called fractional distillation. I'm just going to show you a quick schematic of what fractional distillation looks like. Sometimes when you travel, let's say over towards the prairies, you might see these huge silos, these huge distillation columns, and that's exactly what they're doing. They're taking the crude oil, they're taking this mixture of a whole bunch of different size hydrocarbons, and they're trying to separate them off. They're trying to separate the lightest ones from the heaviest ones. In this case here, when I dig out the petroleum products, that crude oil, that mixture of hydrocarbons here, what we're going to do, the larger molecules tend not to be very useful, so we need to refine it, and the process of refining is actually through this fractional distillation. So let me just walk you through how this works here. We're going to take the crude oil that I dig out of the ground. This contains the C1 to, let's say, argue to C200 or so. first thing you want to emphasize here is all of it gets heated. Okay, so we try to vaporize all of them. Some of them came in as gases, some of them came in as liquids at first, but we're heating it up. On a textbook, we will see about 400, 500 degrees or so. That's usually hot enough to overcome those London forces, those dispersion forces. It's enough to make all the gases transfer through the rest of the column here. Now what's going to happen here is now all that big mixture here, now they're all gases, they get shunted through this distillation column. And what's going to happen, we know from our London forces, when we think about hydrocarbons, although carbon does have a slight win over hydrogen, it's not big enough to be a polar compound. We always say hydrocarbons are nonpolar. They rely on those London forces, those background attractions between temporary dipoles and instantaneous dipoles. We knew that London forces are actually stronger the more charges that we have, indicated by the size of the molecule. So what's going to happen is, as this whole mixture of hydrocarbons actually come in, they're all going to rise, right? Gases are going to just steadily go up through the chamber here. We're going to see that the bottom of this chamber here is still on the hot side. So the really heavy fuels here, they're still hot, they're still gases. They manage to rise a little bit, but because their London forces are fairly strong, their melting points are fairly high, their boiling points are fairly high as well. They don't need to cool down all that much, and they've already liquefied. So what's going to happen here is the heaviest out of this mixture here, although they're going to rise a little bit, having been turned to gas, they're going to condense at a much lower layer. The things that are a little bit tinier, so a shorter carbon hydrogen chain, we're going to have weaker London forces, and those ones that are going to steadily rise a little bit higher. Their boiling points are a little bit lower, so they can manage to escape a little bit farther away from the heat source before they condense, and that basically taper it off at a totally different layer. And gradually over time, we're going to be able to taper off many different fractions, and we're being able to pull off the different layers. The heaviest ones here at the bottom, some of them actually form deposits as residues. We're going to see them being used for a nice road material. Upwards of C1 to C4 here, the London forces are so weak, they actually remain gases, even by the time we're back at room temperature. So those ones there are useful. Not so much for gasolines. For the gasolines, we typically want sort of the C5 to C10. Those ones here are sort of the best fuels. They are liquid, so they're easy to store, easy to transport, more safe to work with, and they also provide that high energy source for me. Turns out when I do this fractional distillation, we don't manage to get a lot of the C6 to C10 that I need to run my cars and automobiles. After we go through a section on octane number, we're going to have a look at how can I chemically take some of these lighter things and make them C5s to C10s, or some of these slightly heavier things, break them, or what's called crack them, to form these C6, C10, those sort of ideal fuels that we need. So they're going to go over again. The longest chains here have a relatively relatively high boiling point. So even though they're on a lower layer, it doesn't take much cooling, and they've already liquefied. While the shorter chains here with the lower boiling point, they manage to get much farther up, and they get condensed at a much higher layer. We talked about shorter chains. They get higher because they have a relatively lower boiling point. They can manage to escape, get higher from the heat source before they actually condense. So they separate this crude oil here now into different fractions. That's why I refer to this as fractional distillation. As we do start looking at sort of fuels and gasolines, things like that, we then come up with a term called octane number. Octane number is something that I can qualify for a fuel in describing how well the fuel itself burns. So this would be our next big idea in this section here. The tendency for a fuel, although fuel for, like if you put gas into your car, although you want that fuel to burn at a very consistent rate, you want to control when the pistons are sort of enlarged or closing. We want to be able to control the rhythm at which when the fuel burns. Some fuels are prone to what's called auto-ignition. Auto-ignition meaning even without the piston, without your engineering and things like that, it just tends to catch fire, it just tends to burn just sort of on its own. Obviously, that already becomes a safety hazard, but more so, your pistons may not be maximally spread out, and maybe the fuel has already burned, and it's not actually delivering the amount of energy that your engine was designed for. This tendency to auto-ignite is typically called knocking. It tends to actually make a knocking sound from the engine. That's why it's called knocking. And it's related, in this case here, to the molecular structure measured by our guy called octane number. So those of you that start driving here, when you go to your gas station here, you see gasoline is rated at different octane numbers. These 87, upwards of 94. These ones here are actually the quality of the fuel itself. Obviously, a difference in cost as well. Note, although let's say a 94 octane number we're going to see is a better quality fuel, not all cars are engineered to run off the high quality fuels. So basically when you buy a car here, if you read the manual, it'll tell you what specifications your engine was designed for. Basically put in the fuel that's your engine was designed for. You could risk damaging your engine if you put fuel that's too high quality or too low quality, because your engine may not be designed for that specification. So let's have another closer look at octane number. For octane number here, a fuel in general, it burns well, it burns efficiently when you supply it with the correct amount of oxygen. So we know oxygen is always needed for combustion. Basically, it's a ratio between the fuel and the oxygen. This part here is defined by the stoichiometry. If my stoichiometry says, let's say methane and oxygen should be in a 1:2 ratio, if I put 1 part methane and 2 parts oxygen, that's ideal, that's complete combustion, that's going to generate the best amount of CO2 and water, and as well energy that's released from there. We could have a situation, however, especially in an engine, we could have a situation where we have too little oxygen. A low oxygen versus a high fuel mixture is referred to as a rich fuel-air mixture. If you don't have enough oxygen here, they ask you a question here in Unit 5, we had called this partial combustion. Partial combustion, although oxygen is used as a fuel source, we don't fully get oxidized to form the full CO2. We tend to get a dirtier flame with unburnt soot, that's the just amorphous carbon, and also carbon monoxide, which is poisonous gas. So if you don't have enough oxygen, there's too much fuel to burn, it doesn't burn that well, partial incomplete combustion. If I have too much oxygen, it can sort of snuff out the fire as well. In that case there, we call it a lean fuel-air mixture, because in this case here, we don't have enough fuel, we have way too much air, and in this case here, it tends to produce a lot of this auto-ignition, a lot of this knocking. In general here, if I have a straight chain hydrocarbon, out of fractional distillation, if I end up with a lot of straight chain alkanes, if I just burn those straight as fuels, they tend to be very prone to knocking. Technically, if I have more branching, we're going to see with more rings as well, they're going to tend to be able to knock less, so they're going to tend to be better for our fuels, and we're going to basically qualify an octane number based on, is it like something that knocks a lot with a straight chain hydrocarbon? We're actually going to use heptane. Let me just flip to that slide here. Heptane, experimentally, it's a 7-carbon alkane. This one here, because it's so straight, this one here actually tends to burn really, really poorly. So this one here tends to auto-ignite, it tends to catch fire just by itself, and tends not to be at the rhythm that your engine necessarily wanted it to be. So we're going to define heptane as having an octane number of 0. It burns really, really poorly. Experimentally, we're going to see in general, things that are more branched tend to burn better, and we're going to set one of them as a reference. We're going to call this chemical a couple different names. In total, it actually is 8 carbons, so it is actually an isomer of octane. However, it's called an isooctane. Actually talks about this particular structural isomer. If you really want the IUPAC name here, we're talking realistically, it is just a pentane. It's 5 carbons as the longest chain, but we have 3 methyl branches branched off at 2, 2, and 4. So this is just experimental. We find that straight chain fuels tend to burn really poorly. We chose one of those as heptane. We're going to call that 0. We found one that was branched. These tend to be fuels that burn better. We're going to call this 100. And basically, I'm going to define an octane number to talk about, well, does it burn sort of like heptane or sort of like isooctane? Let's say I pump in fuel. I pump in 87 gas here. And a gas that's greater at 87 is like a fuel that burns 87% mixture of isooctane and the rest, the other 13% heptane. The fuel itself is not isooctane, it's not heptane, but if I had made that mixture, it burns like that would burn. The isooctane should have burned really well, but since I only had sort of 87% of this one here and only 13% that's heptane, it might be a little bit of a lower quality fuel than, say, isooctane pure 100%. So definitely the higher the octane number, the higher the fuel rating, also comes with a higher price tag. I'm just going to show you one other slide here. Remember, out of this fractional distillation, out of this natural boiling point tendency and condensing at different layers, we don't tend to produce a lot of our C5s and C10s, which we want for fuels. What we can do is chemically, we can do a reaction called the cracking process. And cracking actually involves changing things that are too heavy or too light into the sort of the ideal of the C5s to C10s. So this is just introducing the terminology. We're going to see this much more in the next lesson. So cracking and reforming are 2 ways I can improve the quality. I can improve the octane rating of my fuel. And basically what I'm doing is I'm changing molecular structure, I'm taking straight chain things, and I'm trying to make them more branched, and as it has more branching, it tends to break better. We're going to see an example of thermal cracking. In this case here, basically involves heating it up. So this is not heating to distill it anymore. I've already done that. I've already separated off maybe a C8, in this case a C18 chain here. If I apply heat to it again, in this case here, we can actually use that heat. Cracking means taking a big molecule and making smaller molecules. We're going to see I can take larger molecules here and I can break them to form smaller alkenes. I can get closer to the C5 and the C10 that I want. Again, we're going to do more so on this on the next lesson. Let's just switch over to our textbook and have another look at some of these concepts on octane number as well as this fractional distillation. All right, so this was section C2. This one here, it started off just with the definition here on fossil fuels. I just want to review with you this sort of umbrella term here. Fossil fuel, so far we've said, fossil fuel is a non-renewable energy source, although it does produce high-quality energy. It's a finite reserve. Fossil fuel is sort of an umbrella term. This was actually on the backside already. But fossil fuel here, it's talking about a whole mixture of our coal, the crude oil that we're talking about separating in this lesson here. We even throw in natural gas, so methane. We're going to see in tomorrow's lesson that's a very clean gas to burn as well. Sometimes crude oil is sort of interlaced with sort of petroleum products, petroleum categories as well. Basically, all those names are sort of different types of fuel. We're basically looking at energy that's stored in chemical molecules. And in this case here specifically, we're taking a look at crude oil. When I dig it out of the ground, it comes out as such a big mixture. We saw that fractionating column here. Here's just another schematic of it. Let's go through a few extra details from your textbook. So, looking mainly at this crude oil here. This crude oil here, unfortunately, when you dig it out of the ground, is this complex mixture here. Some of them are straight chains, some of them are branched. You can make a note to yourself here. Straight chains are prone to something called knocking. We'll see that on the other side here. Branching tends to be maybe higher octane numbers. So that's a good thing to note here. A better quality fuel is usually something that has more branching. We're going to see having rings and having even aromatics, benzene sort of functionalities as well. That'll also help with the octane number later on as well. We talked about here specifically for the petroleum products from earlier. When I have decomposition from marine creatures, these are also trapped under high temperatures, high pressures. They do qualify here. These are, because they're buried so deep, they typically are acted on by bacteria in anaerobic conditions. When I say anaerobic, aerobic means with oxygen, anaerobic means without oxygen. So there's a little bit more detail there talking about, well, sure, this decomposed, sure, it's going to lose oxygen fastest and we produce hydrocarbons here. This one here, so far from the comic strip, this part here tended to produce more of the petroleum products, also sort of mixed in. Petroleum is also somewhat of an umbrella term here, talking about its own products as well as crude oil. We pump these fuels here, or we extract them from underground reserves. We may need to transport them to a processing plant, and even after it's processed, after we harness the electricity, we tend to need to transport it many places, so it can actually get to the people that actually want to use this electricity. One big idea we're going to see is every time we do an energy transformation, let's say in this case here, we're starting from oil, and then we're converting it, converting it into maybe heat energy first to turn turbines, heat energy maybe to form electricity. Electricity is a nice sort of very versatile source. We can send it long distances through our electrical wires, things like that. But we're going to see from the last lesson, although again the quantity is conserved, the total energy store that the oil had is passed to the heat, passed to electricity. But given the amount of heat lost to the environment, we're going to have a less than 100% efficiency. Make a note to yourself here, the quality is degraded. So although, fortunately for us, even though we had to process this and refine this and separate the fuel, we still managed to get a lot of the energy, but with every transformation, we tend to lose a little bit along the way. Which is why if we had an option, if I can design a sort of energy transformation pathway, I want to choose a pathway that requires less transformations. I know every transformation will tend to lose energy, but if I have less of these conversions, I'm going to lose less, means I have more to spend later on. These crude oil here has overtaken coal, so just coal, just regular as a like an amorphous, maybe peat or anthracite kind of material. Crude oil has sort of overtaken in terms of the world stage here. It's also a non-renewable source, but it tends to provide a lot easier to work with, maybe more economical, not as expensive, maybe less political, easier to work with, even though it takes this extra fractional distillation process. This crude oil here can also be used as what's called an organic compound feedstock. A feedstock is sort of like a primary, like, oh, these are the raw ingredients you have to work with. You can mix these in however way you want, and it can end up forming the polymers and different pharmaceuticals you want. So it's useful for organic chemistry as well, useful for a lot of research later on. So in this lesson here, we talked about crude oil. One of the primary impurities that we want to get rid of are sulfur impurities. Sulfur impurities, they introduced to you H2S as one example. There's probably other examples like SO2s, things like that as well. But primarily they say here during this process, without going through all the steps of the mechanism, they're showing you H2S here tends to block an active catalyst site. A lot of these reactions here tend to take place too slowly, so we do need catalysts on a lot of these mechanisms here. They're just qualifying here. H2S tends to interfere with the catalyst, and it interferes with how the catalyst actually interacts with the oil. We'll see examples of this catalyst later on with zeolites, things like that, but so far we want to take care of this H2S problem. So here they're giving you an example of how this H2S here is actually removed. There will be some examples, some reactions that I just introduced as we go through the textbook here. I'll try to point out to you the ones that you want to know better, you want to be memorizing. In this case here, this is just for information. So we're going to take this acidic H2S, this is our impurity, we're going to dissolve it in basic K2CO3, so acid-base neutralization. So the H2S that would have been an impure thing that's inside our crude oil, we reacted with K2CO3. Hey, wait, where'd the K go? We know it's an alkali salt, so this is going to be K plus and CO3 minus 2. It's only that CO3 2 minus, that's a weak base that I need to react away the acid. It's going to take the proton. It forms HS minus, HCO3 minus. That's what I'm going to do in one step in one area of the processing. And then what I'm going to do is I'm going to reverse that process in another area. Remember, we have to sort of work in the sort of engineering aspect here. Let's say this crude oil gets pumped in on one side. The H2S here might later on interfere. Maybe at this point here, I do this carbonate treatment. I convert it first to HS minus. So then it doesn't interfere, the reaction can continue, and then later on somewhere, maybe I'm going to take the HS minus, and I'm going to reconvert it back into H2S. So because this is an equilibrium, I can shift this equilibrium back and forth. You can use Le Chatelier to control that. When I then, at another place on my power plant, when I then regenerate H2S, I then burn it in the air. So it oxidizes, I react it with oxygen. This time we don't get CO2s because I have no carbon source. I end up getting SO2s. SO2s and NO2s are, we saw primary components of causes of acid rain, things like that. So this is something I do want to not just, oh yeah, let's just throw a lot of SO2 in the atmosphere. I do want to control how much SO2 is actually being absorbed away. One way of doing that is we can desulfurize it back into elemental sulfur. The nice thing is elemental sulfur is actually a solid. I can basically take that same H2S that I was burning, I can react it with the SO2 product, and I can end up getting just pure sulfur, and I can collect deposits and deposit sulfur. This one here is that yellowish powder that you might see when you're driving around. It's just sulfur. Because we are always conscious of the environment here, sometimes, let's say I do this in a huge refinery, huge power plants here, sometimes they engineer some things called scrubbers, and one notion of scrubbers is just they're porous enough, they contain holes and pores for the SO2s here. Instead of just letting the SO2 go, not just collect it as sulfur here, the scrubbers can actually minimize how much SO2 actually leaves the refinery and actually causes more environmental problems. So that's just one way that we can actually refine this gas here. That's sort of a little bit more detailed than just looking at the crude oil itself. Assuming you've done that, assuming that you pulled off some of the sulfur, now what you're going to do is you're going to put this crude oil, this is the part that we're saying. This could be anywhere from C1 to C200. It's a huge mix that you actually take out of the ground. Not all of them is useful for every source. So what we're going to do here, it's important for you to know as you're explaining this, everything gets heated. Okay, heat to boil, entire mixture. The heavy ones, light ones, everything becomes a gas. Some of them were gases already, but we're going to heat them all. What's going to happen now is as they get heated up, the heat source is somewhere down here. It's hottest here, and it's going to gradually get colder and colder. If I have a very long molecule like C200, that one here, we're going to make a note. This one here has very strong London forces, means it has a relatively high boiling point. I know overall London forces are weak, dispersion forces are weak, but these ones here have a high boiling point. Even though they were all gases at this point here, as they get slowly farther and farther away from the heat source, these ones here are going to be the first ones to liquefy. As they condense at this layer, I can taper those off at whichever layer. The ones that are slightly smaller here, right, slightly smaller chain, the London force is a little bit weaker, they have a sort of moderate boiling point here. They might be able to get a little bit farther away from the heat source, but they eventually condense off. It's only the really light ones. I told you before, make sure you note here C1 to C4. So methane to butane. These ones here actually remain gases. So even by the time we're back to room temperature, when it has nothing to do with the heat source, it was actually gas when it came in. It's still gas, and because even though it's really far away from the heat source, even at room temperature it stays gas. So C1 to C4 just goes right to the top. We are primarily interested in the C5 to C10s or so. Those ones there have a slightly longer chain here. Those ones there will actually be liquid. Again, convenient to store, convenient to transport, safe to work with, and I can just fractionate them. I can just pull them off at a different layer. So here's another example. Here are some terms that you may have encountered. So gasoline or petrol. Petrol is just another name for gas. So this is thinking about car fuel. Naphtha as an organic feedstock is used to make other chemicals. Aircraft typically need slightly heavier grade fuels. So this is for airplanes, kerosene. Diesel fuels. Diesel fuels, we're going to find that there is a way to convert biological compounds into diesel fuel. That's what it actually is. So if we can convert what would have been otherwise waste oil and waste biological compounds, if I can convert it to oil, it's not that I can put diesel into any particular car, but if I have a car that runs on diesel or it can run on a blend of diesel versus gasoline, basically the more options that I have, it decreases my reliance on any one type of fuel. So that's the fractionating column here. Some key points, like I said, make sure you tell me that everything is heated, everything is vaporized. Make sure you tell me that they separate because of different sizes, and the reason they can separate is heavy sizes here have a higher boiling point, smaller ones here have a lower boiling point, and I basically condense at many different layers based on whatever use that I want. Small molecules tend to be more volatile, more flammable, tend to be useful more as fuels. Larger molecules are not as good. Residue, some things that actually are solid, I may actually just collect that up. We mentioned, we could just use that as our asphalt for our roads. So here, just some more description. We call the process fractional distillation. Make sure you know that name. We separate into fractions. So this one here is separated into many different portions. But what this primarily is actually just a distillation. You're heating it up and you're separating. Separate by boiling point. It's a physical separation technique because I'm not actually running any reactions. Chemically speaking, I was a C5 before. I'm still a C5 over here. I'm just separated from the other chemicals. So usually they throw around a number of about 400 degrees. That's enough to heat everything. Everything boils off. The things that are small, C4 to C10, make a note that those ones there are gases. The gasoline, the fuel for our car engines, these ones here are actually liquid. Those are the ones that are highly desirable. This is an important note here. It's very convenient. So convenient for storage, convenient for transport, convenient in terms of safety. Right? So just simply, it's a liquid, so it's much easier to work with. The highest demand is those I mentioned, C5 to C10, making the best fuels. They're easily vaporized. If you look at the heats of combustion from yesterday's lesson as well, they tend to have high heats of combustion as well. I mentioned previously, if you just run it through this fractionating column, we don't tend to get a lot of the high quality stuff. So what we're going to do in the next lesson is we're going to talk about how can we take some of these lighter things and actually make some of these ideal sizes. How can we take some of these heavier things, again, crack them to make smaller sizes. I'm just going to introduce to you the term this time, and then we're going to see it more. So you can actually increase the supply of C1 to C12 by doing thermal cracking, using heat to crack the material, and in general, cracking involves breaking down a larger molecule. Take something that's like C16 and break them up to something that's smaller. C10, break them. They don't have to be the same size. There's a little bit more technical note we'll see in the next lesson, but pretty much if it's not the right size, I can crack them into smaller molecules. We're going to leave this latter section here for the next lesson. This is on cracking. Let's just flip over to the next page here, and we're going to take a look at octane number, because we talked about knocking. So knocking here, again, it's a premature ignition. You can also refer to that as an auto ignition. We do want to burn the fuel, but I want to have control over when that fuel burns, when the pistons are actually expanding. This is fuel that's actually burning without the spark from your spark plug. It can end up damaging your engine. It tends to produce a knocking sound from the engine. So that's why they refer to it as knocking. The energy of your exploding and the combusted gas, your expanding gas here, it's not fully applied at the optimum time, and it reduces your efficiency. So what we're going to do is we're going to create that scale called octane number. Experimentally here, isooctane. We talked about isooctane. It's also called, I don't know if they say it right here. Isooctane here is, oh, it's already said, missed it, 2,2,4-trimethylpentane. This one here experimentally is found to burn really well. So this one here is set to be our standard. Our standard is set to burn at 100. Heptane turns out to burn really, really poorly. So heptane is a 7-carbon alkane, so 2, 3, 4, 5, 6, 7. Again, if you burn that, that's going to be a reference of 0. And basically, I've set up a scale between 0 and 100. I can have octane ratings, whatever I want. So they give you an example here. If I have a fuel, octane rating 96, a really high-quality fuel, this fuel, I don't know what it's actually made out of, but it burns as if it were a mixture of 96% iso and 4% heptane. So I'm not actually physically taking these two standards, mixing them and using them as fuels. I'm actually taking whatever propane, butane source or whatever. It's just that the blend, the mixture that I have, it'll burn as if it was good, like 96% isooctane, but it's not perfect octane. It's not 100 octane rating. It has some heptane into the mix. Heptane, it auto-ignites easily. There's a maximum knock, whereas isooctane has a very minimum knock, which is why we set the 0 and 100. There's a lot of research that goes into this octane number here. You can study it based on your engine, the revolutions per minute. They have just some more detail here. They have what's called a research octane number versus a motor octane number. They run the engine at different speeds. It's possible that you have a fuel that actually has different octane ratings depending on at what conditions that you're actually testing it. Overall, this is one key idea. Not only know the reference, the 0 and the 100, make sure you know typically if I have a linear compound, we said linear is bad, so they're introducing here, usually, if something is shorter, or if you manage to have rings, they tend to have higher octane numbers, as well as if I have double bonds, or even throw in a benzene in there, those tend to have octane numbers. Pretty much anything else burns better than linear compounds. Linears have very high knocking and are not a really good fuel to work with. So we're going to see in the next lesson here, how do we perform cracking reactions, cyclization reactions? How can we convert those linear compounds into things that are ringed, things that have double bonds, multiple bonds here? Adding that unsaturation will actually allow it to burn better, allow it to hit higher on the scale here. In fact, it's totally arbitrary where we set the 0 and the 100. So in 1922 here, we have a guy called Migley. This guy here, he found that there's what are called gasoline additives. By putting extra components to the fuel, he actually found that he could increase the octane rating. It had nothing to do with the actual fuel itself. It had nothing to do with like, oh, change the fuel. Oh, I don't want a straight chain. This was adding something totally different. This guy here was called Migley's compound. It was a guy called tetraethyl lead. This one here, gradually by adding this compound, this one ended up increasing the octane number right away. However, the unfortunate thing is because it did involve lead, lead is a heavy metal, so we want to be really careful of it affecting a lot of air pollution. It inhibits a lot of the functionality inside our cars. We have what are called catalytic converters. They take some of the more deadly poisonous gases, puts in a much more stable state. And in this case here, because lead has heavy metal poisoning here, it ended up having some unfortunate side effects here, neurological effects, I'm sure for all people, but your textbook specifically points out young children as well. So there is this notion here of doing gasoline additives, but we do want to watch out the chemistry. We want to make sure that it's safe to work with, not just, oh, yay, it's a high quality fuel and we can actually utilize it more. In this case here now, we actually substitute it. I don't want to deal with the heavy metal lead. Not only is it not very common, it has all these devastating side effects. We find other chemicals that can also enhance the fuel as well. We can actually add methanol. I can actually add ethanol. These ones here are substitutes. They're like the tetraethyl lead. they somehow increase the efficiency, the octane rating of my fuel itself. Because it was totally arbitrary that I set isooctane 100, turns out methanol actually has an octane number 107. Ethanol actually burns even better than isooctane. It doesn't mean we need to restart our scale, things like that. We just need to be careful. It's not like 0 to 100%. 100% isooctane turning out not to be the best fuel. In fact, things like methanol, things like ethanol actually burn even better than this isooctane, this structural isomer of octane, 2,2,4-trimethylpentane. So have another look over those notes there. If you have any questions, just let me know. Thanks, guys.